Let's talk about neural networks. So, neural networks is actually a really old way of doing predictive modeling that emerged from early attempts to mimic how neurons in the brain might work. And at the time, they were really, really hyped up, but they didn't really live up to expectations, and so they kind of died away for a few decades. They reemerged back in the 1980s, where they were hyped up once again, and people thought they would solve all these sorts of problems, but they didn't really, and the hype faded. They died away once again. And just recently, actually, neural networks have been catapulted into popularity once again with the technique of deep learning that is all the rage right now, which is actually proven to be remarkably successful. So let's talk about neural networks, a little bit about their history and how they work. So let's go. All right, so the neural network framework started out back in the 50s with a predictive model called the perceptron. Now, what the perceptron did was basically take a bunch of inputs you can think of as predictor variables, x1, x2, all the way up to xn. And then what it did is it assigned each predictor variable a certain weight. So you created a weighted sum of the inputs, added in some sort of offset, like an intercept term, and then, take that weighted sum. And then if that sum was positive, then you basically predicted that an individual would be the member of the yes class. And if it was a negative number, that weighted sum, you would predict that individual to be a member of the no class. So essentially, the perceptron was just developing a weighted sum of predictor variables and making classifications on whether or not that weighted sum was positive or negative. And you might think that, well, wait a second, that actually sounds a lot like linear regression. In linear regression, our prediction is just a weighted sum of the predictor variables with some sort of offset. The perceptron is a weighted sum of predictor variables with some sort of offset, and it's checking to see if it's less than 0 or bigger than 0. So in effect, the perceptron was kind of like a bad linear regression model for doing classification. So no wonder why it didn't really succeed all that much. Now, people quickly realized that instead of basically this binary classification, taking this weighted sum and saying yes class if positive, no class if negative, that they could actually pass that weighted sum through what's known as an activation function to convert it into some other number in a nonlinear way. People were beginning to understand that nonlinear relationships existed and they were important to capture. So taking a weighted sum and then transforming it with a nonlinear activation function might actually be somewhat productive. So we construct the weighted sum of predictor variables and then pass it through some sort of activation function. The logistic function, where you take e, raise it to some number, divided by 1 plus e raised to some other number. That's the logistic function. That's the logistic activation function. If you use the perceptron with this as the activation function, well, then congratulations, you've actually reinvented logistic regression, where we take, e to the weighted sum of predictor variables and divide by 1 plus e raised to the weighted sum of predictor variables. The value for y is between 0 and 1, and we can interpret that as the probability of having that class of interest. So updating what the neural network looked like, we construct that weighted sum of the predictor variables, add in some sort of offset, get that weighted sum here, transform it in a nonlinear fashion, and out comes our prediction. So there are some choices for what we actually want to use as the activation function. The perceptron originally used the step function, where basically if it was positive, predict 1, negative, predict 0 here. The logistic activation function makes that logistic curve. There's a bunch of other ways to do this activation function. They all look relatively similarly, though. They all have this monotonic increase from 0 up to 1 relatively slowly, so there's really not actually all that much variety. Now, people greatly improved upon this framework, greatly improved on the perceptron, when they realized that, well, we don't have to just work with, say, one weighted sum of the predictor variables. We can construct numerous weighted sums of predictor variables and then combine them in what we're going to refer to as the hidden layer of a neural network. So let me break down what this diagram is showing. Basically, what we have is 5 predictor variables in this case, x1 through x5, and they form what's known as the input layer. That's what the numbers are coming into the neural network. We're going to make a prediction. We're going to do something with them and output a prediction. So in come these 5 predictor variables, and in the hidden layer, we have 4 neurons. Now, in this neuron, what's going to happen is it's going to construct a weighted sum of the predictor variables, and then it's going to transform it in a nonlinear fashion and output that for later on in the network. Now, what's interesting is that each neuron in this hidden layer constructs a different weighted sum of predictor variables. So it's engaging in kind of what we refer to as feature engineering. It's coming up with more useful predictor variables based on what was originally measured. Basically, four different weighted sums transformed in a nonlinear fashion. And what happens is that the outputs from the neurons in the hidden layer get combined once again in yet another weighted sum. That weighted sum gets transformed one more time with an activation function. And then finally, we have output our prediction. So when we use a neural network like this with one hidden layer, we're basically engaging in feature engineering. We're constructing nonlinear predictor variables based on the originally measured values, and we're combining them in a very creative way. And so this is why people got really excited. It naturally models these nonlinear relationships. It was purported to basically be able to solve all sorts of problems that you could throw at it. Now, the upshot was that in the end of the day, that it didn't actually work as well as what people originally thought, but it provided a good groundwork that people kept coming back to and thought, well, how can we actually improve this a little bit more? So here's an example of where a neural network might be used. Let's imagine that we want to forecast what happens to some sort of medical patient. And okay, some things we know about that medical patient might be something about their physical measurements, like their BMI index, their age, their sex, etc. And there might be some additional things that we know about this patient in terms of, let's say, their diagnosis, some properties of a tumor they might have. What we might do is construct a whole bunch of weighted sums of these predictor variables, feed them into the hidden layer of the neural network. They all get transformed. We have 1, 2, 3, 4, 5, 6 different weighted sums being transformed, and then get recombined, transformed into an eventual prognosis. So that's what a neural network is essentially all about, basically coming up with weighted sums of the original predictor variables, transforming them to become nonlinear, recombining them in another weighted sum, transforming them again, and coming up with a prediction that comes out. And this actually forms the basis of deep learning, which you might have heard quite a bit about these days. This is what Google is using to come up with the self-driving cars. Deep learning is really, really good at doing what we call unsupervised learning. And what deep learning is just a very complicated neural network, a neural network with many, many different hidden layers, where the output of each hidden layer is some nonlinear transformation of the weighted sum of the inputs to it. And so you can model some very, very complex looking relationships with very subtle interactions. There's really not much that a really complex neural network can't do. The problem that you run into when you try to do deep learning or really complex neural networks is computational time. And that's why really neural networks back in the 80s and the 50s didn't really succeed all that much. Computers really weren't up to the task of estimating all the parameters that needed to go into one of these neural network models. For each one of these neurons in the hidden layers, they're getting a different weighted sum of the predictor variables. And so you have to figure out the weights at each single stage of this process, and that works out to be a lot of different parameters. So the way deep learning actually takes place is they don't actually use your computer at all to do those computations. They do computations on graphics cards, which are streamlined to do phenomenally complex, very rigorous calculations very quickly. So we don't have the hardware set up to do that, but that's essentially what deep learning is. So the neural network provides a framework for doing predictive modeling. There's some tuning parameters, of course, that you're going to have to figure out what works best for the given situation. How many hidden layers do you need? Well, the more hidden layers you add into your neural network, the lower the bias the resulting model is, because the better it's going to be able to fit that training data, pick up on any sort of subtle relationships it has. But as we know, as we decrease the bias of the model, that's going to increase the variance. It's going to make the model's form very, very dependent on the specific set of individuals that happen to be in the data. So not only the number of hidden layers, but then how many neurons do we want in each layer? How many weighted sums of the inputs do we want to construct and transform in a nonlinear fashion to output for later use farther on in the network? And then also, because you can really easily overfit with a neural network model, because there's so many different parameters to estimate, so much information that you're taking out from the training data to estimate its form. There's an additional parameter called the weight decay, or the regularization parameter, that essentially penalizes the sizes of weights. So you're not allowed to basically take too much information all at one time from a predictor variable or from any particular input to a neuron here. So there are a lot of different ways of constructing a neural network. There's a lot of different packages in R to actually go and construct one for you. We'll talk about a few of them. One really nice one allows you to actually visualize the neural network. So in this case, we're predicting tip percentage based on a few predictor variables: bill, whether or not the gender was male or female, smoker yes, smoker no, and party size. And you can see the weights that are actually going into each weighted sum. So this guy right here, it's getting the weighted sum, minus 14.8, minus 774 times bill, minus 115 times gender male, etc., etc. Then it's passing that through maybe a logistic activation function, and then combining that output from each of those three neurons in the neural network as an additional weighted sum, transforming that once again with a logistic function, and then outputting the answer. So you'll get some practice tuning one of these neural network models. Sometimes it can take a lot of time to do so. It's hard to get the right neural network model, but they very often have some pretty good success. So some pros of neural networks: they can learn very, very difficult nonlinear relationships with relative ease by automatically creating these more relevant predictor variables with those hidden layers. Now, it turns out that neural networks does the best when the distributions of everything involved resemble a normal curve. Another justification for why we like transforming to symmetry here. But we need a lot of data to really have neural networks perform very well. That was another reason why they weren't performing that great in the 80s. Data sets weren't big enough. Computers weren't fast enough. Now the technology and the data has really kind of caught up to where it needs to be. We've seen a lot of success with neural networks here. So once it's trained, the predictions are very, very fast, and this is what the state-of-the-art deep learning is all based on. Now, the cons is that a lot of people aren't very trusting of neural networks because of their past history. They were overhyped early in its history through the 80s, and so people kind of, find a little bit of its claims a little bit hard to believe here. Now, in business analytics, when we're doing predictive analytics here, neural networks actually aren't often the best choice, mostly because a lot of the quantities we're interested in studying don't resemble a normal curve. So those partition models, XGBoost, really the front runner when it comes to business analytics. Deep learning neural networks really good for human-related behavior, like self-driving cars, visual recognition of objects in pixelated images, stuff like that. So here's kind of a fun quote that I liked. Well-known neural network researcher said, "A neural network is the second best way to solve any problem. The best way is to actually understand the problem." That's really the best way to go about it. Really get to the nitty-gritty details about the problem you're trying to solve, and then come up with that relevant model. I would replace neural network with XGBoost. Really, still the best way to solve the problem is to really have a deep understanding of it.